We have plenty of time, so
Okay.
Carmen just get started.
Thank you for the introduction. I'm Shumeng Ma. I received my PhD last year from University College London, and I'm now a postdoc at EU University. I'm glad to have this opportunity to share some of the interesting work I did during my PhD. And today my presentation is about placing low occupancy fragments into the electron density using the anomalous signals of sulfur and halogen items in fragment-based drug discovery. Unlike traditional high throughput screening against small molecules, which with the molecular weight in the range of 300 to 500 Dalton, fragment-based drug discovery works with fragments with a molecular weight below 300 Dalton. Fragments are smaller and they bind weakly to the targets. The purpose of fragment-based drug discovery is to identify fragment hits and develop them into potential drug candidates. So the advantages of fragment-based drug discovery, FBDD for short, is first, its efficiency. Fragments are more likely to interact with the targets, which means we have more fragment hits to work with in the initial stage. Second, fragment libraries have higher coverage of chemical space than small molecule libraries, which means the various fragments represent a vast range of potential chemical compounds. Also, fragments have simpler structures, which makes it easier to understand how they interact with the targets. So in fragment-based drug discovery, we typically start with fragment screening using various biophysical methods, among which X-ray crystallography provides detailed 3D structures, allowing a faster structure-based optimization. In practice, fragments are first soaked into protein crystals, and the crystals are harvested for X-ray data collection, and the solved structures allow us to identify fragment hits and analyze how they interact with the targets. We can then grow, merge, or link those fragments into molecules with the improved binding affinity, better specificity, and with other improved properties. The successful application of FBDD has resulted in 6 marketed drugs, and here listed 3 representative drugs discovered and developed in FBDD. For example, and also their initial fragment hits. So for example, the vemurafenib, which is for the treatment of late-stage melanoma, is the first FDA-approved drug emerged from FBDD. So while FBDD holds significant promise, it also represents unique challenges due to the fragments' properties, such as low binding affinity, the coexistence of alternative binding orientations in the binding sites, and the low occupancy. A large proportion of fragments tend to display incomplete electron density in the maps. Also, because of their low molecular weight and the incorporation of at least 1 aromatic ring, fragments, so it's pretty hard to fit the fragments into the density because a large proportion of them are planar or quasi-symmetric. For example, in our FBD study against SARS-CoV-2 non-structural protein 1, fitting this fragment into the incomplete density gives us 4 possible binding orientations with very close R3 values after refinement. So it's really hard to know which is the correct binding orientation for this fragment. So now I will introduce the approach we used to solve this problem. We employed anomalous scattering of heavy items commonly seen in fragments such as sulfur and halogen items to determine their positions within the crystal structure. So what is anomalous scattering? X-rays at the wavelength close to the absorption edge of heavy items are absorbed by their electrons, causing a unique phase shift in the diffracted X-rays, which can then be used to identify the position of the heavy items within the crystal structure. And then which items contribute to the anomalous scattering? Anomalous scattering is stronger for items with the high atomic numbers because their electrons are more tightly bound, making them interact significantly with X-rays near the absorption edge. Common anomalous scatterers relevant to fragments include sulfur, phosphide, chloride, bromide, and iodine. And then how is anomalous scattering data collected? Synchrotron sources can be tuned to the X-ray wavelength close to the absorption edge of the target anomalous scatterers to collect their absorption anomalous scattering signals. For example, from the figure, we can see the absorption edge of chloride, shown as the green line there, is close to the energy of 2,800 EV, which is 2.8 keV. So when X-ray is tuned towards the 2.8 keV, the anomalous scattering of chloride can be well detected. So now I will show you how can anomalous scattering help determine fragment orientations in the binding pocket. We normally only have the standard difference Fourier map at the beginning, which guides the initial ligand fitting with some uncertainty. Then we can collect anomalous scattering signals for the 3 fragments shown here, and then calculate their anomalous difference Fourier map, shown as the magenta blobs here. We can see the initial fitting is only correct for the first fragment, and for the middle one, there are 2 alternative binding orientations with the sulfur sitting in both left and right sides. And for the third fragment, it should be fitted upside down to let the chloride sitting on the top. Therefore, the integration of standard difference Fourier map with the anomalous difference Fourier map can confidently suggest the binding orientations for fragments. We collected anomalous scattering data at diamond I-23, which is a long wavelength beamline with a semi-cylindrical Pilatus 12M detector and a multi-axis goniometer in the vacuum. We compared the anomalous signal of sulfur from sulfur-containing amino acids and fragments from data collected at 4.5 keV at I-23 and at 12.8 keV from another advanced beamline, ESRF Massive 1. Obviously, the anomalous signal of sulfur can be observed consistently to a high level from the data collected at 4.5 keV in the vacuum. So we chose the 4.5 keV because both the sulfur and other halogen items have sufficient anomalous scattering at this energy. You may want to ask, why do we settle for sufficient instead of maximum anomalous signals? For example, from the figure here, we can, sorry, my pointer. Okay, so from the figure here, we can see the anomalous absorption edge of iodide, shown as a black line here, and the bromide, shown as a magenta line here. So they both have very strong X-ray absorption close to their absorption edge. So when the X-ray is close to their absorption edge, the strong absorption of X-ray may induce the potential radiation damage. For example, the X-ray absorption induced, the radiation damage induced a distortion of anomalous difference Fourier map was observed on an iodide containing fragment when we collect data consecutively from the same crystal using 9 keV energy. And so the top panel here from figure A to F shows the representative changes where a single anomalous blob gradually developed to 2 blobs along the data collection. And the lower panel here shows the changes of an anomalous sigma ratio between the 2 anomalous blobs along the data collection. So one assumption here is the absorbed X-ray induce the cleavage of carbon iodide bond. And as the data collection proceeds, the fraction of cleaved carbon iodide bond increases, as shown in the upper panel. The second anomalous peak becomes bigger along the data collection. So for iodide containing fragments, 4.5 keV can give us sufficient anomalous scattering will mitigate the potential radiation damage. Apart from the anomalous scattering, PANDA analysis, PAN dataset density analysis is also a powerful tool for the identification of low occupancy fragment that leverages ensemble refinement and multi-crystal averaging to enhance the accuracy of electron density maps, revealing subtle differences that pinpoint the binding sites of fragment heats. It has been reported that the effectiveness of ligand binding detection by anomalous scattering is comparable to or even superior to that of PANDA. So it will be interesting to compare their effectiveness in determining the low occupancy fragments in the binding in the incomplete electron density. So we compare the PANDA maps for the 2 fragments of NSP1 showing the figure A and D with the overlap map of standard difference Fourier map and with the anomalous difference Fourier map showing the figure B and E. Clearly, the PANDA maps have a more complete density for the 2 fragments, but it does not confidently suggest the binding orientations for the 2 fragments. With the help of anomalous difference Fourier map, shown as the orange mesh here, we can confidently fit this fragment as shown in the figure C. And in the second case, there's a smaller orange blob and a larger orange blob, which indicates the location of sulfur and iodide respectively, because iodide has stronger anomalous scattering at 4.5 keV. So we can then fit this fragment as shown in figure F. Of course, all approaches have their limitations. Our approach is only applicable to for fragment containing heavy items with anomalous scattering, and it takes longer to collect the data set than the normal data collection. It's approximately 6 minutes per data set of 360-degree rotation with fine slicing. But with the more sensitive equipment and better experimental conditions, collecting anomalous scattering data from lighter item might be possible in the future and in a faster way. To wrap up, anomalous scattering data collection at a dedicated long wavelength beamline is beneficial for the confident determination of correct binding orientation for low occupancy fragments containing sulfur and halogen items, and is complementary to PANDA. This is crucial for subsequent binding pattern analysis and structure activity relationship study to guide structure optimization in FBDD. Finally, I would like to thank my previous supervisor, Frank Kozlowski, our previous group members, and our collaborators from Diamond I-23 and ESRF Massive 1. Thank you all for listening. I'm happy to answer any questions.
Thank you, Shumeng. Really, really interesting. We have any burning questions coming? We have a few minutes. We have a bit of time. I have a first question maybe to kick off things. So you said you collected that at the SRF at 12.8 kV and also the I-23. Did you try to do anything with the ESRF data and see if there was any anomalous, or did you try to explore other energies like 8 or 9 kV, not as extreme, so that this could be done more routinely?
Yeah, we also we precise the data collected from ESRF at 12.8 kV to see the anomalous signal from sulfur, but there's a lot of noise in there because the at 12.8 keV anomalous scattering of sulfur can barely be detected, and also it's the data collected in normal way is not being vacuumed, so there's a lot of noise at the back to affect the calculation and the results. So it's for sulfur, I think it's more doable in I-23. For iodide or bromide, those heavy items, it's you can see those anomalous signals at 12.8 kV. But the problem, as I mentioned, is the radiation damage. So at high energy, you might have a very high X-ray absorption, and that might be a problem to cause like a distorted anomalous map.
People have solved structures of sulfur sat at 6, 7, 8, even 9 kVs. So I think maybe it would be a bit more comparable. Yeah, 12.8 is quite extreme to see sulfur.
Yeah. Yeah, you mean collect data at 7 kV for sulfur?
Yeah.
Yeah, it's just for fragments. If we collect data at a single with a single energy, it would be easier just in one go to see all those items.
Thank you. Okay. So, question here.
Thank you for your talk. I was wondering, in your study of the iodide fragment, your radiation damage study, I'm sorry if I missed it, but what's the dose for each data set?
Oh, we collect data at 9 kV consecutively from the single crystals. We collected for 22 data sets just from the single crystal, and to see the process of anomalous difference map changing along this process.
Yeah, well, never mind. Your extra, the extra blob for the iodide, do you ever fully populate it? Can you reach a point where you cannot see its original position in the anomalous signal anymore?
We tried to collect data at 2.7 kV where we cannot see the anomalous blob from chloride, but so we already know there's a chloride in the fragment, so we know the type of the items is chloride, so we don't need to do this identification below the absorption edge and above to see what kind of items is there. So that's not the purpose of the study. Thank you.
I think there is a question on Slack. If you
Yes, there's actually, it's more a general question about fragment screening or not. So if the active site is deep inside the protein, can you still do fragment screening if your active site is rather buried? It's more a general question about fragment screening and feasibility of it.
My understanding is yes, because the fragments are generally very small, so they are more easily to get into the deep pocket. But it really depends on how deep this pocket is. Is it exposed to the solvent channel or to solvent? And like it really depends on the case. Thank you.
Okay, if there's no more questions, so we thank Shumeng again, please.